Okay, I think we are finally ready. Welcome everybody to the set theory seminar. So today we have an in-person speaker again, which is exciting. On the other hand, it poses some challenges, strictly speaking, but I think we're ready. So Jonathan Osinski is here, and he is going to speak about model-theoretic characterizations of weak Vopenkas principle.
Yeah. Thanks for the introduction. If at any point the sound is bad for the people on Zoom, please just say something. I think we don't really know how good it is. So, yeah, let's see. Okay, so what I'm going to talk about is basically quite recent. So, like, I'm based in Hamburg normally, but like I'm on a US trip right now, and basically I'm going to present some results I had during the last weeks. And some of them are with Will Boney from Texas State, and some of them are with Trevor Wilson from Miami University. And okay, let's see. So, okay. Yeah, we're going to talk about weak Vopenkas principle, and well, this is some form of weakening of Vopenkas principle, which is basically this statement. So, for any proper class of K of structures in some fixed vocabulary, there is an elementary embedding between two distinct members of K. And when this was introduced, like in the late 60s or 70s, it was quite fast clear that this is rather, like, even though it's a bit unusual for a large cardinal principle, because it doesn't really directly talk about large cardinals, was quite fast being shown that it lies in consistency strengths between the existence of an extendable and the existence of a huge cardinal, just very roughly to an idea. Okay, and then what's kind of interesting about it is that it has quite some different equivalent formulations, and some of them are from category theory. For example, the following, that was shown by Adamek, and Shrimkova. Vopenka's equivalent is equivalent to the statement: the category of ordinals cannot be fully embedded into the category of graphs. So, what do we mean by that? So, category of ordinals just like as objects as ordinals, and as morphisms we have just inclusion. And then
and you consider the ordinals with the epsilon relation, I mean with their less than ordering, or?
Yeah.
Yeah.
Okay, but also I'm not really going too much into like this category theoretic characterizations anyway. This was just a motivation to introduce the weak Vopenkas principle. Later we will actually work with like some different equivalent characterizations. I'm just presenting this like some kind of history. Okay, well that means that like we have some sequence of graphs such that indexed by the ordinals, such that for ordinals alpha less or equal than beta, there's exactly one homomorphism between the graphs G alpha and G beta. Then for some alpha smaller beta, there's actually a homomorphism back, so from G beta to G alpha. Yeah? Okay, and this result kind of motivated the following definition of weak Vopenkas principle, that the dual category or an op cannot be fully embedded into the category of graph. Yeah? So this means if we have some sequence of graphs indexed by the ordinals, now that for every alpha less or equal than beta, there's a homomorphism from G beta to G alpha, before that we have the other way around, then we have to find some alpha smaller beta that there's a homomorphism from G alpha to G beta. Okay, and I don't know, like it was shown to have some implications for category theory. For example, this statement here, I don't know what it means. It's just it was one of the things those category theorists were able to show. Every subcategory of a locally presentable category is reflective, and they also were able to show that it actually had some large cardinal strength. So they were able to show that it implies the existence of measurable cardinals. So there seems to be at least like some kind of interesting principle, because it's like quite a natural variation of this equivalent formulation of Vopenkas principle, and it has applications in both category theory and large cardinal theory. So this is quite nice. And it's very easy actually to see that Vopenka's principle implies weak Vopenka's principle. In fact, we can show this. If we have Vopenka's principle, then for any sequence of graphs indexed by the ordinals, we have some homomorphism from the alpha to beta for some alpha smaller beta. And this is like the conclusion of the formulation of weak Vopenka's principle. So that's the Vopenka's principle, and that's the weak Vopenka's principle. Okay, the proof is very short, so let's look at it. So first of all, observe if we have that, if we would have for some proper class C subset of the ordinals or subclass of the ordinals, that the cardinality of all G alphas in that class is the same, then we would have to have that G alpha is isomorphic to G beta for some smaller beta, because there are set many graphs of some cardinality modular isomorphism. Okay, so we can just, without a lot of generality, assume that G alpha is actually smaller than G beta for smaller beta. And then by Vopenka's principle, we get an elementary embedding. Now, just like the graph considered as like a first order structure from G alpha to G beta for some alpha, which is distinct from beta. But we cannot have alpha larger beta because then F couldn't be injected. It would have to be as an elementary embedding. So alpha has to be smaller than beta. Okay. So then people thought maybe that weak Vopenka's principle could actually be equivalent to Vopenka's principle, but for a long time there was not really any kind of advancement in that. In that question, but recently Trevor Wilson showed that weak Vopenka's principle is actually equivalent to the statement art is wooded, which is weaker than weak Vopenka's principle, because, for example, witness in V delta for some wooden cardinal delta. So this was like the solution to like what the exact large cardinal strength of the weak Vopenka's principle is. And yeah, I'm not going to go into what art is wooden, like what wooden means. Again, we will look at a different formulation later, but to get an idea now. Okay. And now actually what we're going to want to do is to get like a characterization of weak Vopenka's principle in terms of properties of strong logic. And yeah, mean by that. So we want to look at compactness properties. So given some logic, so by that I mean like, I'm not going to define it, but what we mean is like some extension of first order logic by, for example, additional quantifiers or infinitary logics or second order logic. And okay, so we say kappa is a cardinal, then the logic is kappa compact if every less than kappa satisfiable. So if we have like some theory and all of its less than kappa size subsets are satisfiable, then the theory has to be satisfiable. Okay, and we just call the smallest cardinal kappa, such that some logic is kappa compact with compactness cardinal of L. And on the other hand, so in a second I'm going to talk about like how Vopenka's principle can be characterized in terms of properties of strong logics, and it can also be characterized by some actual large cardinals, and those are Cn extendable cardinals. So what's that? Like we write Cn for this class here, for the class of all ordinate alpha, such that V alpha is a sigma n elementary substructure of the universe. And this is like, you can show that quite easily. That's basically the reflection theorem, that's the club class of the ordinals. And then the cardinal kappa is Cn extendable. If for every alpha at the kappa, there is some beta, such that there's an elementary embedding from the alpha to the beta with critical point kappa. J of kappa is then beyond alpha. This is just the normal definition of extendability. And then to make it a Cn extendable, we demand that J of kappa is in Cn. Okay, and then it was shown that already by Markowski in 1985 that Vopenka's principle is equivalent to the scheme every logic has a compactness cardinal. While with logic we mean like what I here call set presentable logic. So we kind of have to we don't want to look at things that are called like class-sized logics. So logics that have for some given vocabulary possibly classed many sentences or sentences that are not bounded in size by some cardinal. So we only want logic that have so like this. And on the other hand, Joan Bagaria showed around 10 years ago that Vopenka's principle is also equivalent to the statement for every n there is a Cn extendable cardinal. Okay, and then on the other hand, this can even be made a bit more sharp. Like one can actually show that the Cn extendables are precisely the compactness cardinals of some specific logic, so-called the sigma n fragment of sort logic. I'm going to talk about that a bit later. For now, just observe we can actually have like not only this like global result of Vopenka's principle is equivalent to every logic has a compactness cardinal, and for every n there is a Cn extendable cardinal, but we also have like some more local version of the Cn extendable cardinal precisely are the compactness cardinals of some logic. Yeah. Okay, and now our goal is in a second I will talk about how Joan Bagaria and Trevor Wilson actually showed that weak Vopenka's principle also has some kind of large cardinal characterization, like the Cn extendable characterized Vopenka's principle. And what we want to do now is to also get a characterization of weak Vopenka's principle in terms of compactness properties of logics. Okay, and first of all, so what this characterization that Joan and Trevor came up with for weak Vopenka's principle is they showed that this is equivalent to the existence of so-called pi n strong cardinals for every n. So what we want to do is we want to take an existing characterization of strong cardinals in terms of compactness properties of logics and turn that into a characterization of so-called pi n strong cardinals. Okay, and for that, to introduce, like, I just want to show you what the characterization of strong cardinals is. So this year we have to remember what a Henken model for second order logic is. So suppose we have some tau structure for some vocabulary tau, so some set of relation symbols, function symbols, and constant symbols, and we have some second order sentence over the vocabulary. Then Henken structure that is a model of that sentence is just the structure M with an additional set P that is a subset of the power set of M, so a set of subsets of M. And we say that the sentence phi is true in that Henken model if it's true when we reinterpret all the second order quantifiers to only range over the set we picked out. Yeah. Okay. And with this, Will was able to show that cardinal kappa is lambda strong if and only if the following holds. If we have some theory T in the logic which is second order logic with infinitary conjunctions and disjunctions of size smaller than kappa, and we also have an additional quantifier in it, the well-foundedness quantifier. Let's forget about this for a second. And this theory can be written as some increasing union of theories that are indexed by kappa, such that all of those have models of size at least kappa. Then this whole theory has not a model, but a Henken model that has as its universe some ordinal at least kappa, and where this Henken part of the model contains at least all subsets of M of rank smaller than lambda. Okay. And yeah, like I said, we want to generalize this to get some characterization of high end things. And well, yeah. So with this, I will come back to this slide later. So basically, what we have to add is like we have to add some properties of the Henken model, and we have to look at a logic that is stronger than second order logic to get this characterization. Okay. Good. Now let's talk a bit about those pi-n strong cardinals. And first we need some notation for that. So given some class A, and the class shall be defined as the formula phi of x, and if we have then given some elementary embedding j from B to M, then we just write j of A for all A and M such that M believes phi of A. So we just write j of A for M's version of A. That's some notation. And then, okay, given a natural number n and an ordinal lambda, the cardinal kappa is lambda pi n strong if for all pi n definable classes we have, first of all, what we would expect for strongness, like an elementary embedding from B to M that has critical point kappa, and where M contains V lambda. And additionally, we demand that A intersected V lambda is contained in J of A. So M knows about all elements of A which are below lambda, or which have the rank below lambda, that they are in A. Okay, and then the cardinal is pi n strong if it is lambda pi n strong for all lambda larger than kappa. Okay, and then what you can do with those pi n strong cardinals, you get like a nice level by level analysis of weak Vopenka's principle. If we do the following, so if we look at weak Vopenka's principle, where we restrict to sequences, there are two different versions of weak Vopenka's principle. One is with sequences of graphs, one is with sequences of structures in a fixed vocabulary. They are just equivalent, it doesn't matter. So let's stick with the graph one. So the pi and weak Vopenka's principle is just where we restrict to sequences of graphs that are pi n defined. Yeah? Okay, and with this, Trevor and Joan were able to show that pi n weak Vopenka's principle is equivalent to there is a pi n strong cardinal. And of course, like weak Vopenka's principle is equivalent to pi n weak Vopenka's principle holding for all n, and so we get like the weak Vopenka's principle is equivalent to the existence of pi n strong cardinals for every n. Sequence definable by n.
Sorry, the sound has got a lot distant suddenly.
Okay, still, or was it only like some?
That sounds better actually. Sorry, now there's no sound at all.
Well, was Andreas Blass trying to ask a question or just coughing?
Yeah, if there's a question, let's
I,
interrupt.
I was not going to ask a question, but I would like to hear what's going on, which I can't now.
Now?
Can you hear anything now?
Is it okay? Or do
I
we have-
can hear very faintly. It sounded like Gunter was saying something. I think you're better. I think it works better for the speaker, but not well for anyone else.
Okay, like, I mean, yeah, we moved it closer to me, so maybe I guess that's better than it working better for anybody else, or
This just now was great. So yeah. But now it's completely gone again.
Same here.
yeah, we're thinking now if we can change the audio on the slide to a different device. I'm not
And then
sure.
everyone has to come back in. If they don't know.
I mean, it's
Not necessarily like,
Yeah, it would be okay, like you have at your room on your.
yeah,
I mean, now it sounds very good again.
yeah, it's just very inconsistent, I guess.
Because now you just sit, you can just sit down in front of the room screen. The sound should be
All right.
fine.
I
Okay.
don't care.
Yeah, but this is the issue. When it was with the laptop, this is why I was kind of secretly hoping the owl wouldn't be here. It's much better if the person is just sitting in front of the laptop.
Okay, we're trying to switch to laptop.
Maybe you can just-
Yeah, I guess. Yeah, I guess I need the Zoom link.
Yes.
I don't have it myself.
Okay, full interruption. No one will hear us.
Yeah, it's-
No, I don't have it.
I can try to send it to you provided I have connections and say to them, oh, now Google account is telling me, great. Okay, I don't think I have connection, but can you can you forward and it's the.
Maybe Yuri can
the
send me
seminar
the
reminder.
Zoom link.
Oh, yeah, I can just forward it.
Exactly, that's what I was.
Yeah. Shall I send it to your email? To your email?
Yeah, but things like Gunter is anyway.
Yeah, well, so what's your email?
Ja, Jonathan.Osinski
Okay. I've just sent you an email as well.
No, it's there.
Yeah,
Okay. Ah, yeah, okay. I have it by Yuri.
But by the way, right now, the sound works pretty
Yeah.
okay. And including the people in the back. We can even hear what you're talking in the audience. Although now we can't again. So I'm not sure.
So I guess we have to take like
So maybe
turn the owl
something is
off now,
broken
otherwise
with
there
the
will be
owl.
like some weird
Yeah.
feedback, I guess.
It seems that when someone in the Zoom starts talking, then the sound in the owl disappears for a few seconds afterwards.
Okay, I guess now it should be better. Is that true?
Okay.
Okay.
I guess now I have to share my screen. Just,
So I didn't say that.
yeah, still feedback. A bit, I think.
Do you want to turn it off, period?
Here we have.
I mean, how does it work? How do you turn it off? I don't know.
You unplug it,
You can, yeah, plug it.
but then you have to. This where the cord goes. Thing. Good. Oh my God.
Is it working now? I think.
Yeah, yeah, I
Yes,
think.
I think
Okay,
it's working.
good.
Okay.
Then I only have to open my slides again. And this here. So where are we?
So I'll stop the share here.
Okay.
Now the slide has disappeared.
Yeah, because we're switching to my laptop screen now. Okay, now they should be there again.
That's very good.
Okay. Okay, seems to work. Okay, so where were we? Third attempt, I think. Okay, for some natural number n, and if lambda is actually a limit point of Cn, then kappa is lambda pi n strong is equivalent to, there's an elementary embedding that has critical point kappa, v lambda is a subset of m, and m is a model of lambda is in Cn. And third, for every pi n definable class A, there is some elementary embedding, again, critical point kappa, v lambda is a subset of m. And this time, not A intersected v lambda is a subset of J of A, but actually A intersected v lambda is precisely J of A intersected v lambda. Okay, and yeah, so basically this says M is correct about A below lambda. Yeah. Okay, and I actually want to show you the proof on the one hand because it's quite short, on the other hand because there's one thing that I want to point out about it. So suppose we have like this this embedding given by, or not quite. So suppose we have kappa as lambda pi n strong, then we can observe that Cn is actually pi n definable, so we can use the lambda pi n strongness for Cn. Yeah, so this means we get an elementary embedding J with critical point kappa. V lambda is a subset of M, and Cn intersected V lambda is a subset of M's version of Cn. Yeah. Okay, so that means for alpha smaller than lambda in Cn, M knows that alpha is in Cn. And because lambda was a limit point of Cn by assumption, we have that M is a model of lambda is a limit point of Cn because yeah, M knows about the alpha below lambda that are in Cn. And because Cn is a club class, as I said earlier, then also M thinks that lambda is in Cn because it's a limit point. Okay. And now 2 to 3. So given J as in 2, so where M believes that lambda is in Cn, if we have a pi n class that is defined by some formula phi of x, and if A then is in V lambda, then, well, this just means if phi of A holds in V, then V lambda is a model of phi of A just because lambda is in Cn. And this is just equivalent to M believes that phi of A, because also M believes that lambda is in Cn, which just means that V lambda is a sigma n elementary substructure of M as well. Okay, and 3 to 1 is clear because, well, this was just like a stronger statement in 3 where we have like the equality instead of the inclusion. Okay, and now notice that here in the proof, the one time where we used like, where we chose A to be some class, we actually chose it to be Cn in 1, where we, in 1 to 2, where we, yeah, there we chose A to be Cn. So what we actually showed was those 3 things that we had before are actually equivalent to the 4th thing here. There is an elementary embedding such that this precise exactness condition holds just for the class Cn. And then maybe some of you noticed, like I never said anything about like where the critical point goes in those embeddings. Like often like in strongness, you will find like the definition that you have J of kappa is larger than lambda, but this is actually not needed. Like we can add it or we can leave it out. Yeah. So in all those characterizations, we could add that J of kappa is larger than lambda. Okay, and then one more thing. So strong cardinals are, of course, if you want to get like some ZFC definition of them, you define them in terms of extenders, and you can do the same thing, and that's what Joan and Trevor did for pi and strong cardinals. So you can show that they are like that cardinal is lambda, pi, and strong if there exists some specific extender. And once we have this this characterization, we can observe that this extender lives like in some initial segment of the universe. So then we can actually not look at elementary embeddings of the universe into some class, but we can actually look at elementary embeddings between set size structures. So what we then get is that, for example, and I picked this one here because we will use this one here later in the proof, that if we get some elementary embedding from v lambda plus 1 to some transitive set M with critical point kappa, v lambda contained in M, and Cn intersected v lambda is the image of Cn intersected v lambda, then kappa is lambda, pi, and strong. And maybe one thing to notice here is like normally we had like J of Cn was like M's version of Cn. What we mean here is actually like what J does on the set Cn intersected v lambda, which is an element of v lambda plus 1. So yeah, this is a slight difference between those two characterizations. Okay. And now let's look at the logics we actually want to consider to get our characterization. For this, normally you would look at something that is called sort logic. That was introduced by Yoko Vernon in the 70s. And basically what it does, it can define precisely the sigma n union pi n classes. But sort logic is a bit complicated to introduce. So what we will do now is to actually look at a slightly weaker logic. And to introduce that, let's first just fix some notation. So suppose we have just some logic and some formulas in that logic, phi with like one free variable and psi with two free variables. And if we have some like structure, then I want to write a phi for just all elements of A that satisfy phi. And similar, I want to write a psi for all elements of A that satisfy, like for all pairs AB that satisfy psi. Okay. And now if we have a natural number n, and then we define some logic Ln, and this will be an extension like of second order logic, and we just add one quantifier. And okay, this quantifier is a bit complicated, but we get through it. So this quantifier takes three variables, x, y, and z, and two formulas, phi of x and psi, dependent on the next two free variables. And we say A is a model of this whole sentence if, well, the subset of, or the substructure of A, which has as its like carrier the subset of A defined by the first formula, and as its relation the subset of A squared defined by the second formula, if that thing is basically isomorphic to some V alpha, where alpha is from Cn. Yeah. So this logic can precisely, well, like recognize if some definable substructure of it is isomorphic to some V alpha, where alpha is from Cn. Okay. Is that clear?
That's formulated very in a complicated way. It just means, right, that this A phi is isomorphic to some D alpha.
Yeah, exactly. Yeah. Yeah, that's what it means. Okay. And then the other thing, like, notice in this characterization of strong cardinals by Will, we talked about Henken models for second order logic. And what we want to do now is talk about Henken models of this logic we introduced here. So we have to come up with some other notion. And this is basically what I'm going to do is something that is from a paper by Will, Stamatis Dimopoulos, Vika, and Menachem Magidor. They introduced the Henken model just for a general given abstract logic. And the idea is kind of, if you think back of what a Henken model for second order logic is, then this is kind of as, it's kind of like evaluating the just second order logic sentences in some model of set theory where you work with some with some model of set theory that is incorrect about the power set of the structure. Like we just look at like in the Henken structure, we have just some arbitrary subset of the power set, and if you think of this as being in some like not correct model of set theory, then this is like evaluating the second order statement in that model. And this is just the idea for Henken models for some abstract logic. So given some theory T in some logic, and now what we mean by logic, we mean like something that is definable by some formula of set theory. Yeah, so we have like some satisfaction relation of the logic, and this should be some relation between structures and sentences of the logic, and we should be able to write down some formula that defines this relation. Yeah. Okay, so given the theory in the logic, a transitive model of that theory consists of, well, just some transitive set, then some relation, which is just the satisfaction relation of the logic reinterpreted in our transitive set, and some designated element n, such that for every formula phi of t, M believes that n is a model of phi. Yeah. So this is like evaluating the logic in some possibly not correct model of set theory. Okay. Good. And then given such a model, we want to just, yeah.
So the T is the set of sentences, which itself could be complicated, right? So you want those all to be like available in M, or
like the sentences should be in M, but the theory itself doesn't necessarily have to be.
I mean, but the theory is a set of sentences, right?
Yeah, it is. But it could be that all sentences are in M, but T itself is not.
I see, yes, right.
Yeah.
So T is just the sub.
Yeah.
Yes,
Yeah.
okay. Okay.
Well, somebody drew something on the. Not sure. I mean, I can also just ignore it.
Yeah, look at view option at the top.
There's a view option.
Oh.
Okay, sorry again.
Okay.
Okay, whatever. Okay, let's just fix some notation. Yeah, so we say M is full up to some ordinal lambda if V lambda is contained in M. Yeah. So in the carrier of the Henken model. And we say M is n correct for some set A if for all elements of A intersected M, it is correct for all sigma n formulas. Yeah? So basically it's correct for the sigma n formulas for all elements of M intersected with A. Okay, clear? Good. Okay, and with that we can get we can state our theorem. So kappa is lambda, pi, and strong. And now for lambda, a limit point of Cn. That's why we talked about this characterization before. If for every theory T in the logic, so we have second order logic, we again have this kappa means we have infinite disjunctions and conjunctions of size smaller than kappa. Then we add our quantifier QCN, and we also add this well-foundedness quantifier, which is true of a formula if it defines some well-founded relation. Okay, and let's call this logic Ln. If we can write T as an increasing union of theories indexed by kappa, then if all those T alphas have models of size greater or equal than kappa, then T has such an Ln Henken model, so a Henken model of this logic we picked out, such that this designated element that is kind of supposed to be our, like the model of the theory, has size at least lambda, and M is full up to lambda and N correct for V lambda. So it contains, so M contains V lambda as a subset, and there it is correct about the sigma N formulas. Okay. And the proof will be kind of similar to some characterization of wooden cardinals from this paper, where also the Henken models for abstract logics were defined, which is, I guess, not so surprising because those, yeah, I mean, weak Vopenkas principle, as we said earlier, is equivalent to Ort is wooden, so it's not so surprising that this will be similar to some characterization of wooden cardinals. Okay, so let's first prove 1 to 2. Okay, so suppose we have such an embedding, and oh no, not such an embedding. Suppose we are in this like situation where we have T, and T is the union of theories T alpha, and they all have models M alpha, and they all are of size at least kappa. So notice if you have models for some theory, you can also just get Henken models by putting them into some correct model of set theory. Yeah. So we can look at a function f on kappa such that f alpha just picks out some Henken model of T alpha. Yeah. And we just make this Henken model look like this. We like take some universe V B alpha, and then the rest we are kind of forced to choose in a specific way. This is the satisfaction relation of our logic reinterpreted in VB alpha, and this is our actual model of T alpha M alpha. And we just choose those B alphas in Cn, which we can do basically because if you're correct about all, like our logic is definable by some, I guess, I'm not sure if it's a sigma N or pi N formula, but one of the two. So if VB alpha is correct about this, it will be correct about this model being a model of T alpha. Okay, and notice because so they are all of size at least kappa, we have that B alpha. All the B alphas will be also of size at least kappa. Okay, now we use our lambda, pi, and strongness. So we get like some elementary embedding, J from B to M, critical point is kappa, J of kappa is larger than lambda, B lambda is a subset of M, and M believes that lambda is actually in, or M knows that M is actually in Cn. Good. Now observe J is, so F is a function on kappa such that F of alpha is a Henken model of T alpha. So J of F is a function on J of kappa such that in M, J of F of alpha is a Henken model of some theory T alpha star, where J of T is the union of all alpha smaller J of kappa of T alpha star. Okay, then all the F alphas are Henken models of T alpha. So in M, we will have that J of F of kappa is an L Henken model of the union of all alpha smaller kappa then of J of T alpha. And this will be a superset of, well, the union of all the alpha smaller kappa of the J pointwise image of T alpha, and this is just J pointwise image of T. And now, I mean, here I'm lying, here I claim J pointwise image of T just is T. I'm lying a bit here. It's not quite correct. Like, so notice that the sentences of our logic, they are all of size smaller than kappa, so they live in V kappa. And the critical point of our embedding is kappa. So what J does on those sentences is what it can rename the non-logical vocabulary of the sentence, but it doesn't change anything about the sentence other than that. So basically, so the pointwise image of T is T modulo some renaming of the non-logical vocabulary. So let's just, for simplicity, assume that it's T. And okay, M is correct about the structure here being a Henken model because, well, being a Henken model just means that M star believes that N is a model of the theory in question. And this is just a first order assertion. So M will be correct about this.
So what is the thing with the vocabulary? I mean, so altogether only how many symbols occur in T anyway, right? So you could not assume that the symbols that occur are also elements of T kappa. If you make that change, then it will be
no, the theory T could be large, like it could contain a lot more sentences.
So it's
T is like a union of kappa many theories, but those can have any size. So T could contain more than kappa many, like sentences in T could contain altogether more than kappa many symbols.
okay,
Yeah. Okay, so M thinks this is an L Henken model of some theory that is a superset of T. So it is actually a Henken model of T. Okay, then all the F alpha are full up to rank alpha. So M believes that J of F of kappa is full up to rank J of kappa. And M might be wrong about this because it might contain not the correct Vj of kappa, but it contains the correct V lambda. So it will be correct about this up to rank lambda. So J of F of kappa will actually be full up to rank lambda. Okay, and then left to show is that J of F of kappa is n correct for V lambda. So let A be in M star, which was like the carrier of the Henken model, intersected V lambda, and phi of x some sigma n formula. And we just have to show that M star is correct about A, like phi holding of A or not. Okay, notice like the F of alphas were all had its carrier as some beta alpha for beta alpha in Cn. So M will believe that M star equals V beta for some beta in Cn. Okay, now we have that V is a model of phi holds of A, if and only if V lambda is a model of phi holds of A. This is just because lambda is in Cn. Then this will be equivalent to M believes that phi holds of A. This is because M knows that lambda is in Cn. Then because M believes that M star is some V beta for beta in Cn, this means that M believes that M star is a model of phi of A. And this just means M star believes phi of A, because this is first order satisfaction here. Okay, here, sorry. Okay, and that's the first direction. Good, and now for the other one, suppose we have compactness like there. So we want to use this lemma we stated before, so it is sufficient to get some elementary embedding J from V lambda plus n to n, to some n, critical point is kappa, V lambda is contained in n, and we have this correctness about Cn. below V lambda. Okay, and for this we consider the following theory. There will be stuff coming later, but I first want to say something about this. So we look at the elementary diagram in the logic L kappa omega of V lambda plus 1. So if we have a model of this theory, this means that V lambda plus 1 is an elementary substructure of it. Yeah. Then we look at this here. So we add a new constant C, and those C index I or kappa, those are supposed to be the constants that are used like in this elementary diagram. So we add this here, it says Ci is smaller than C is smaller than C kappa for all I smaller than kappa. And basically, if we have a model of this means this model has to add some element between Ci and C kappa, which means that it has to move kappa. So kappa will be the critical point. And then, I didn't say, so what I mean here is this Magidor's phi. So Magidor in this like old paper where he showed that, for example, second order logic is the LST number of second order logic is the first supercompact cardinal, constructed the sentence of second order logic such that the models of that sentence are precisely the structure is isomorphic to some V alpha. Yeah, so this sentence we add here. Yeah, so a model of this theory here will be an elementary superstructure of, or like V lambda plus 1 will be will elementarily embed into it. It with critical point kappa, and it will be isomorphic to some V alpha. Okay, then we add this the sentence with the well-foundedness quantifier that just says our epsilon relation is well-founded. Yeah, so to get a well-founded model. And now we add two sentences that say something about this, that shall basically express this condition here, this correctness about Cn. So we add like, if X is in the constant C of Cn intersected V lambda, so notice Cn intersected V lambda is some element of V lambda plus 1, so it has like some constant appearing in this elementary diagram. So if X is some element of the, well, of the element of the structure that interprets this constant, then we say, well, basically then Vx is in Cn. That's what this quantifier says. Yeah? This quantifier was able to, like, yeah, tell when a structure is in Cn, and this we just put here. Yeah, so if X is in Cn intersected V lambda, then this quantifier just says X really is in Cn, Vx really is in Cn. And now we add a second sentence, which is basically the converse of that. Yeah, so like if X is such that Vx is in Cn and X comes from V lambda, then X will be the interpretation of the constant. Okay, now we can write T as an increasing union of satisfiable theories, T alpha, by basically by looking at this part of the theory. Like if here we for alpha smaller kappa, we only look at those I which are smaller than kappa, then we can just make V lambda plus 1 a model of this theory, because those other things are all true in V lambda plus 1. Okay, so by 2, we get an Ln Henken model, which looks like this, which is full up to rank lambda. It's n correct for V lambda, and it has this n part of it has size at least lambda. Okay, so then because of the first part, this elementary diagram part, we have that M believes that this map defined by sending like the constant Cx interpreted in V lambda plus 1 to the constant Cx interpreted in n is an elementary embedding. This is just a statement about first order formulas satisfied in either structure. So M is correct about this. So this is really an elementary embedding. Then we have the critical point is kappa, because, well, so it has to be at least kappa, because, sorry, at most kappa, because by this part of the theory we have that kappa is moved. And because L kappa omega can define all ordinals below kappa, they actually have to be fixed. So this means the critical point is precisely kappa. We have that M believes that N is a model of phi. So this means that N is the V beta, like M thinks that N is some V beta for some beta, at least lambda. Because by like M might be incorrect about this because it might have like above V lambda not the correct V betas, but at least this will mean that V lambda is a subset of N because V lambda is a subset of N because V lambda is a subset of M by this fullness up to lambda condition. Okay, so the only thing left to show is to have this correctness about Cn. And now notice by the two sentences we added, we have that M believes if alpha is smaller than lambda, then M believes that N is a model of alpha is in the interpretation of this constant, if and only if N believes that this quantifier holds of basically the structure V alpha. Yeah. Okay. N is a model of this here just means that alpha is in J of Cn intersected V lambda, because that's how we defined our map. And M believes that this quantifier is true of the structure here means that for some reason I always go further before I want to. So yeah, that M believes that N is a model of this quantified statement here means that, well, M believes that V alpha is such that alpha is in Cn. So M is a model of alphas in Cn. Okay, and because M is incorrect about V lambda and alpha is smaller than lambda, we have that then alpha actually is in Cn. And if we put that all together, then alpha is in J of Cn intersected V lambda. If and only if alpha is in Cn for all alpha smaller lambda. So overall we have this. Okay, and this is what we had to show. Okay, now I'm gonna, like, this is now like a bit stupid, I guess. we can like, if we put this weird Henken model compactness into some definition, we can, for example, say that for some natural number n and some ordinal number, the cardinal kappa is a n lambda Henken chain compactness cardinal for a logic L. If every theory that can be written as an increasing union of theories that all have models of size at least kappa, then T has an L Henken model that is like we had before. As like this n has at least size lambda, and m is full up to lambda and n correct for V lambda. And if we put this, then we get like a statement that is equivalent to weak Vopenkas principle. That namely that weak Vopenkas principle is equivalent to, for all natural numbers n, all again set presentable logics have for all ordinals lambda an n lambda Henken chain compactness cardinal. And this kind of resembles this equivalence of weak Vopenkas principle to all logics have a compactness cardinal. Okay. So this was compactness cardinals. And now I want to look at basically the other part of the other important property from model theory, which is Löwenheim-Skolem properties. And again, for quite a long time, it is known that that Vopenkas principle is also equivalent to some statement about Löwenheim-Skolem numbers, namely something I will get to in a second. So first of all, a cardinal kappa is called the LS number of some logic L if it is the smallest cardinal kappa such that all sentences of L have some model of size smaller than kappa. And it's called the LST number of L if all sentences of the logic and all structures that are models of that sentences have some substructure of size smaller than kappa, that is a model of phi. Yeah. Okay, so if a logic is set presentable, one can actually show in ZFC that it has an LS number, because being set presentable basically just means there can be only set many sentences, and then you just look at the supremum of all sizes of models that satisfy one of those set many sentences, and this will be an LS number for the logic. But on the other hand, Starby proved in the 80s, I think already, that Vopenka's principle is equivalent to all set presentable logics have an LST number. So this LST number actually gives large cardinal strength. Okay. But now, so I said now all set presentable logics have some Löwenheim-Skolem number. But actually, Trevor recently showed that if you go to class-sized logics, the LS number of logics can have large cardinal strengths. And in particular, he showed the following. If you look at the fragment of infinitary second-order logic, so this here, L2 infinity infinity, means like second-order logic with both or all four conjunctions, disjunctions, universal quantifiers, and existential quantifiers of all infinite sizes. So if you look at the fragment of this, in which all sentences are in negation normal form, and in which we only allow disjunctions and universal quantifiers of infinite sizes, and all the conjunctions and existential quantifiers are finite, then the LS number of this logic is the first strong cardinal. Okay, and yeah, basically, him and me, we generalized this again to include statements with this, well, either of sort logic or with this quantifier that's allowed to or able to talk about the class Cn. So if we look at the fragment of infinitary second order logic with that quantifier added, in which is like the before mentioned one, all sentences are in negation normal form, and disjunctions and universal quantifiers of infinite size of all infinite sizes allowed, but not any finitary conjunctions and existential quantifiers. And the quantifier Cn only take finitary formulas. Then the LS number of this logic is the first pi n strong cardinal. And yeah, if you're maybe, I'm not sure if there are many people around, but if you're used to talking about sort logic, you can also show some version of this for sort logic. Okay, and then as a corollary, we again get weak Vopenka's principle is equivalent to every now possibly class-sized logic L that is at most as strong as one of those logics we looked at here, has Löwenheim-Skolem number. Okay, and that's basically the end here. Maybe some things to do or open questions. I only learned about this a few days ago, actually, but there is like some other notion of Henken models, which was specifically designed for sort logic. It was introduced by Yoko. And I don't know, I'm kind of sure that this characterization, this Henken chain compactness characterization can also be worked out for this other notion of Henken models. So this is something that could be checked. Then, yeah, you can look at other fragments of this infinitary second order logic, or also of infinitary first order logic, and some properties of those are still unknown. And I guess the most pressing one is, what is the Löwenheim-Skolem number of, before we look at second order logic with those infinitary disjunctions and universal quantifiers, but what is the Löwenheim-Skolem number of first order logic with infinitary disjunctions and universal quantifiers. And then, yeah, if you think about those logics, you can also think about adding, like, basically what I said now was supposed to say something about allowing vocabularies where the relation symbols have finite-arity. But if you can quantify over infinitely many variables, you can also think about infinitely, relation symbols of infinite arity. So, yeah, and now, so basically the proof of this result here does not really work if you allow, relation symbols of arbitrary arity. So this would be something to think about, like, in which, like, can we add those relation symbols of arbitrary arity? Does it change the large cardinal strings, or does it stay the same, or is it maybe even inconsistent? I don't know. So yeah, those are questions that one could look at. And yeah, basically I'm done. So thanks for attending. No, nobody can hear you.
Yeah.
I have a question. So what is this Henken model notion of Yoko's?
Yeah, maybe I repeated, like Vika asked what the Henken model for sort logic is that Yoko introduced. Basically, it's just you add another set, like you add a set that the second order variables quantify over. You add another set, but the set, not a class, that the sort variables are able to quantify over.
Oh, I see.
Yeah. So I think if you just adapt the proof where you put in like we had lambda in a limit point of C, and maybe if you just put in V lambda there, or maybe just some other V alpha where alpha is sigma n correct, then you should be able to do everything that you want in this like initial segment. So I feel like this should just work.
Okay, I see.
Yeah.
Mhm.
I have a kind of just a very vague question, and that's that, you know, when you talk about the Vopenka principle in the very beginning, it was just a proper class of structures.
Mm-hmm.
Then you talk about the weak versions, and all of a sudden it was sequences of structures indexed by ordinals,
Mm-hmm.
which kind of seems like there is some influence of some global axiom of choice or something like that. Like, does something like that play a role? Like, if you have the full Vopenka principle, or are there versions of weak Vopenka principle where you don't talk about linear, linearly enumerated structures or something like that?
I mean, honestly, I'm not quite sure. I don't quite know about those category theoretic formulations of Vopenka's principle. I guess if you like, I'm pretty sure that you can do all of this if you want to in like some GBC class theory or NVG class theory, and everything should work out. Like normally there's like nothing that goes wrong, like in switching between like those perspectives, just everything definable at ZFC and going to some class theory. So I think if you're worried about that, you could just carry out all of that in GBC, I guess.
Which really has.
Yeah, which would have global choice. Yeah, true.
So the question is whether there are some subtleties that you don't have that.
So I think the answer is no, and I'm trying to remember what the reason is. So they are equivalent, the formulations. And it goes through something or another, and I don't remember at the moment what it is, but you don't need to. Because this is something that.
There is this result, I think. GBC is conservative over.
Yeah, you can definitely add, but I think you just don't. It somehow you can go from the characterization where it's only for these enumerated collections to any collection. And I'm trying to remember what the reason is. So I don't think you need to somehow say, okay, I can get global choice somewhere else. It's that I just don't think it needs global choice for the equivalence. But I have to look this.
Okay.
Because this bothered me at some point, and I remember looking into it, and I don't remember what I remember resolving this that it doesn't need, but I have to look back at that.
Something like together all the structures of a certain rank and change the language or something. Okay, well, let's just like this.